Okay, so Abelian varieties. It's absolutely wonderful to be here again, to see this wonderful, marvelous crowd of people and Bear, and to be given the exercise, as I was given, to talk about Abelian varieties to all of you. Now, when I told that to a friend, she said, not a mathematician, she said, Abelian varieties? And I went on with that as the real theme of my program, but it isn't. Let's see whether I can deal with this. Oh, I'll deal with it this way. So, what are Abelian varieties? Why are they interesting? Why are they useful? I suppose that's the exercise I was given to try to explain it to this audience. It's going to be the theme of my lectures. Why are they interesting? Well, there are so many different, not only reasons, but directions to pursue reasons. The simplest is what they are is an extremely important class of algebraic varieties, of which rational varieties, rational varieties and general type varieties and other types of varieties play a big role in classification. They're not only close to every one of those other classes, especially Calabi-Yau varieties, but that's not why they're interesting. That's just something you say if you want to begin the discussion of why they're interesting. They're also useful, and they're useful in so many domains, but I'm going to take a specific one, and that is, if you take the problem of finding rational points or talking about or understanding the structure of rational points on curves, well, that's a question that's been with us since Diophantus, and an extremely hard question. And one of its very, very powerful tools is Abelian varieties, which comes in some sense to the aid of comprehending the structure of rational points on curves, and we'll get to that. But the other thing that is awesome in trying to give a talk at this moment about the subject is that it's moving very, very fast. For example, there'll be slides where I write theorem something, and it's definitely a theorem, but you can't keep up with the pace. Almost every one of my theorem somethings that you're going to see has been expanded, elaborated on in very, very many ways. It's moving fast. And it's not only moving fast, but it's moving in new directions. For example, there's a guy in the first row who I'm going to cite. For example, we have now I would call it a classical tradition of databases for elliptic curves. But what about Abelian surfaces or Abelian varieties? In the grandeur of that database or elliptic curves, there's no match at the moment. But there's a beginning of such for Abelian surfaces. And another thing I want to say is I'm giving another lecture at the end of this program. Anybody who wants to offer suggestions to me by email in the interim for current work on computation in terms of databases for abelian varieties, do email me, and I'll try to make some sort of coherent commentary about that. But I also want to choose the usefulness of abelian varieties for curves as my basic direction of talking about them from beginning to end, and especially the new and burgeoning sort of, let's call them subfields of arithmetic, uniformity issues in Diophantine equations, and what's sometimes called arithmetic statistics. I'll begin hinting at that, and at my second lecture talk more about it. But if you talk about abelian varieties, you might as well begin with dimension 1, that is, say, elliptic curves, and I'm going to think of elliptic curves defined over fields. And they're all representable as plane curvics, in some way representable or other, as plane curvics, plane cubic curves with coefficients in K. Starting in the spirit of Weierstrass. So if you're given a lattice, I'll call my lattices lambda in the complex numbers, that is a discrete subgroup, free, of course, of rank 2 in C. Weierstrass defines his Weierstrass function, an amazing doubly periodic function, depending on the lattice, and essentially invariant under translation by the lattice. And these are, that colored picture below is the picture you can find on the web of the phase spaces of the values of this P of Z, what's called the Weierstrass P function. Now, the Weierstrass P function doesn't live alone. It comes along with its derivative. And if you consider the pair, well, you consider complex numbers parameterized by the pair, the value of that Weierstrass P function and its derivative, you discover that you're no longer in analysis, complex analysis, but you're also in algebra. That is to say, it parameterizes the affine cubic curve that I've displayed there, where the coefficients, G2 and G3, are given very elementarily in terms of the lattice that the Weierstrass P function depends upon. Now, that's true because of the relationship between the Weierstrass P function and its derivative, this boxed equation there, the format of equations for elliptic curves. And it does this absolutely amazing structure. It gives this quotient, C mod lambda, which is born as a complex, if you want, a complex Lie group. It gives it an algebraic structure. That leads the theory to two directions, to complex tori. Let us say any compact, complex, analytic abelian Lie group, which is of the similar form, let us say complex G space for some G divided by this lattice, which in that space would have to be, well, discrete free abelian, but would have to be of rank 2G, so as the quotient to be compact. Not all compact, complex, analytic abelian Lie groups have the virtue that they do when G is 1, that is to say that they're directly related to algebraic structures. But the theory is also leads to the other direction, which is the direction that we're going to talk about, abelian varieties. And in Weierstrass's case, at least, to elliptic curves, to cubic plane algebraic curves with an inherited group structure. It also moves very smoothly to the more modern spirit of Poincaré. By the way, are there topologists in the audience? No topologists? Whoa, okay. Well, even if you're not a topologist, take a look at Poincaré's paper where he, so to speak, does something about the Poincaré conjecture. And you'll discover that, oh, I mean, he's a blithe spirit. I mean, you don't see anything like what we think of as the Poincaré conjecture. And there's a similar blithe spirit in his work in arithmetic and algebra. As I say here, there is hints of the cubic plane curve structure that Weierstrass discovered for lattices in the work of Jacobi a bit before this, but it really was in Poincaré's 1901 paper where elliptic curves, i.e. one-dimensional abelian varieties, got started. Here's a quote from it. I'll give you my translation. Rational points on cubics. This is Poincaré in his paper. Let's first study the distribution of rational points on these curves. I note that knowledge of two rational points on a rational cubic is sufficient to get us to know a third. Actually, he writes faire connaître, which means I could also be get us acquainted with. Okay. For example, if you happen to are acquainted with P and Q in this picture, you get to know the point R on that cubic by drawing a straight line between P and Q and looking for that third intersection point. If you continue to do this in an unlimited fashion, you get what's called nowadays, well, no, sorry, what was called the chord and tangent process. Is that a standard thing that people know about this? Okay. Somebody does. It used to be called the chord and tangent process when I was a kid. Okay. Okay, now without stating any of this explicitly, Poincaré views the set of rational points on an elliptic curve as an abelian group. And he has no proofs at all in his paper. He just talks beautifully. He defines the rank of one of these things. I call it an elliptic curve here on this slide. He defines the rank of an elliptic curve to be the number of points playing the role of P and Q needed to get all the rational points on the curve. Now that's his formulation of it. And he assumes that the rank is finite. Assuming, therefore, anticipating a theorem that was only proved 2 decades later by Mordell. Now there's age doing its work in these 2 pictures. So Mordell, I like his, on the rational, the title of his paper, on the rational solutions of the indeterminate equations of the 3rd and 4th degree. Well, you and I know what that means. You know, rational points on cubic plane curves. Okay. And he does prove if a non-singular rational plane cubic curve has a rational point, the group of rational points is finitely generated. Now, how does he do it? He does it by descent. He called it descent, and we call it descent. And here's how I formulated it. If A is an elliptic curve over Q defined by one of those indeterminate equations of the 3rd or 4th degree, and A of Q is its group, which it turns out to be commutative, of rational points, then the way in which descent works, which is Mordell's proof, and as I'll comment in a few minutes, is everybody else's proof who extends this picture. It has two parts that play off one on the other. Okay, I just call them, I don't know whether this is standard. I'll call the first weak Mordell-Weil, and I'll call the second controlling by height. So weak Mordell-Weil is just proving that you're trying to prove that A of Q, that A of Q is finitely generated. So why not start by proving that A of Q over 2A of Q is finite? That would be a good start. And weak Mordell-Weil is that start. And then you control by height by proving that, or noting that, multiplication by 2 increases the height of a Q rational point, essentially by a factor of 4. So if both of these things is true, and the height you're taking is sort of a slightly more sophisticated height than what Mordell took, it's called Néron-Tate height, by 2, it follows that a rational point of non-zero Néron-Tate height can't be divisible by arbitrarily high powers of 2. And so, therefore, given 1, a simple further argument proves that A of Q is finitely generated. Now, what's great about this is that they're surprisingly computable, or at least surprisingly computable in upper bound. So A of K over 2A of K is what Mordell worked with, and he gave a bound, and as I say, it's a very computable one. More generally, now we do the same, prove the same sort of proof, but we allow ourselves to take A of K over NA of K for other n's. But it's the computability of those upper bounds that's the strength of Mordell's original proof and of everyone else's elaboration of it. As I say, this is echoed by all the later proofs of the more general Mordell-Weil theorem. And they all make use of this, which are called the fundamental short exact sequence. That is to say, if you have an abelian variety, if you have an abelian variety and you consider multiplication by n, and take its kernel, which is the elements, if you wish, or the subgroup in the abelian variety that's killed by multiplication by n, so you get an exact sequence. You take the long exact sequence of cohomology of this exact sequence, and you cut out what you're interested in, namely the fact that the thing you're trying to bound is at least contained in this group. Well, that's good as far as it goes. The cohomology of K with coefficients in the n torsion of A. But it doesn't quite get you where you want, because this is very likely infinite rank over Z mod NZ. So you have to be a little subtler. You have to impose local conditions. Now, what do you mean by imposing a local condition? It means you're interested in considering the subgroup of H1 of K with coefficients in the n torsion of A that could possibly be the image, or possibly contain, if you want, the image of this. Well, if it contains the image of that, it'll have to contain the image of its localization for any prime V. So impose that as a condition on H1 of KAN, this possibly infinite rank group, and it cuts down as you throw in more primes, V, and you cut out what's usually called the Selmer group. They're called Selmer groups. And these Selmer groups are not only finite, but they're computably finite. And that gives you the weak Mordell-Weil with a computable upper bound. Okay? That's where our subject started, but there are now, the subject has an incredible tradition, and of course in an hour I will not do anything but put a finger on one piece of that tradition or another, but there are milestones. And here's one, which is simply a computation. The elliptic curve with the highest rank, this is over Q, over the rationals, found so far is this monstrosity. It starts with perfectly sane coefficients, pluses and minuses, and then its constant term is that three-line red digit, and it has rank, I say, at least 28. I think there's more talk about that in the literature if you want. And this was by Noam Elkies, so one could call that the Noam Elkies elliptic curve. And now, if you have something that is of rank 28, should you be impressed, or should you say, so what? Well, Park, Poonen, Voigt, and Wood say you should be impressed. Why? They use random matrix heuristics to formulate a very precise conjecture, and therefore it's a conjecture that depends on our believing in some mystical sense that however we constructed our elliptic curves and their rational points and so on, they're done in some, they follow some procedure that is in some sense random if you can frame the procedure appropriately. And if that's the case, what they conjecture is that there are only finally many elliptic curves over Q of Mordell-Weil rank greater than 21. So you should be impressed with that 28. It seems to be one of the finite big, I need a good label for a curve with a really robust Mordell-Weil rank that distinguishes it from the infinitely many other elliptic curves there are. What's interesting is read their paper. I mean, it's a beautiful paper. And the other thing that's interesting is they make no further actual conjectures. And I asked Melanie why, and she said, well, so if she made any further conjecture, I think I'm not at liberty to tell you because she didn't really give me anything precise. But at least she had the sense that, yeah, there are other conjectures that could be made. Now, we're talking about abelian varieties. I don't know. Looks like it's an interesting question. Who knows? I mean, could you do this not for elliptic curves, but for abelian varieties of dimension G, where the 21 would be replaced by, who knows, 21 to the G. But I'm not, she said nothing of that sort. And even I said nothing of that sort. You keep it quiet to this room. Okay, but anyway, it's worth computing. And maybe we'll talk about possibilities for computing in the next lecture. I said in the beginning that I wanted to push for issues of uniformity and average and statistics. Now, what's now called arithmetic statistics is a real field, and with wonderful, as I write here, it has immense literature. Okay, and the simplest to state qualitative conjecture that's still outstanding is that roughly half of the elliptic curves of a Q have more delta rank 0, and half have rank 1. And those, well, of course, and those with higher rank amount to, I write 0%, but that 0% should hide perhaps, if they're up to the first x, there's some sort of polynomial, possibly in log x, that accounts for that 0%. As I say, it's an immense literature, and I can't even begin to ascribe attribution to it appropriately, but I'm sure if you Google exactly this, you'll begin to get sources that are worth reading. So that would imply that the average rank of Morel Bay is a half. Now here are the things that are known and easy to put on a slide. It's known that if you arrange elliptic curves, the question is when you say half is this and half is that, you have to order the elliptic curves somehow. And everybody has their favorite way of ordering elliptic curves. So you're going to order them by a maximum of the various powers of the coefficients of the cubic equation. Are you going to order them by their other things like their conductor? So there are various techniques for ordering. But if you arrange these elliptic curves by a certain naive height, the average size of the 2-Selmer group that I described before is 3, and the 3-Selmer group is 4, and the 3-Selmer group is 4 result alone implies that the average Mordell-Vary rank of elliptic curves of a Q is less than or equal to 7.6. 7.6 is far from a half. Here are some papers which you can look at, but the field is moving very fast, and 7.6 has been improved. Okay, abelian varieties in general. It's curious. I mean, I keep scratching my head about this. You need very few axioms to define this. We have a whole winter school about abelian varieties, and then the question is, how do you define them? Well, here's a sparse definition. I'll be over a field. If I wanted to be over a scheme, I could do that too, but I'll be over a field. And I want to start with A over K, a smooth projective variety. Okay. And a point. Called it E, a K-rational point. And all you have to suppose is that there's some sort of morphism from A cross A to A. You and I know it's going to be the group structure on the abelian variety, but axiom system doesn't know anything. Just a morphism from A cross A to A, defined over K. And I'll write it as multiplication for the moment. Later it will be addition. And relative to which that multiplication law, relative to that multiplication law, E is the identity element. That is, say, X times E. That is, say, X comma E sent to A by taking M of it, M of XE, is X, is E times X. That's enough. It's an abelian variety. What does it mean? Well, there are basic theorems. Abelian varieties are, in fact, abelian algebraic groups. Multiplication is a commutative group law, and so naturally we change the multiplication sign to be addition to make it look like more commutative, if you wish. And there's not only one proof, there are a number of neat proofs of this. Well, two of them, there are actually more, in Mumford's book, Abelian Varieties. And I'll give you a piece of the proof, and you'll see how, it's kind of beautiful. I don't know. For example, I want to see that the morphism has inverses. Well, you consider the mapping that sends A cross A to A cross A, I'll call it phi, by sending the couple xy to x times y, comma x. Now, the inverse of EE here can only be EE here, if you think of it, right? So the inverse of EE is a point. That is, say, the fiber, I'll put it geometrically. The fiber of phi over EE is 1 point. But phi maps a variety of dimension, twice the dimension of A, to itself. So by standard dimension theory, you have to have that phi is surjective. So for any x, there's a y such that xy is E. Really neat arguments of similar nature gives that M is commutative and associative, slightly longer arguments. And that, of course, once we're in abelian variety territory, we are dealing with the spirit of André Weil. When I say spirit, I didn't mean it to be a loaded word in any way, but what I meant was we're talking about a coherent subject, abelian varieties, and in various phases, it's attacked by people with such completely different sort of attitudes towards mathematics, towards proof, and towards subject. Okay, the spirit of André Weil. I say, although it's his theorem, it's called the Mordell-Weil theorem, the result that generalizes Mordell's theorem is usually stated in the following way. If K is a number field, A an abelian variety, then the group of rational points of A over K, called the Mordell-Weil group of A, is a finitely generated abelian group. But they actually didn't prove it that way. He proved it specifically for abelian varieties that are Jacobians of curves, and that's good for me because that's going to be the next topic of my little talk here. He stated this way: one finds, this is Weil, one finds that all rational systems of points on a curve are derived from a finite number of them by addition and subtraction. Okay? To be more modern about this, a rational system of points is a divisor on a curve. Derived from is linearly equivalent to. That's our modern vocabulary. And it leads us to the particular class of abelian varieties that are Jacobians of curves. Because what they proved really is that an abelian variety that is the Jacobian of a curve has a finitely generated group of rational points. But happily, any abelian variety over K is isogynous to a sub-abelian variety of the Jacobian of some curve. So the Mordell-Weil theorem which they initially proved, oh, well, he proved both at the same time, but his first step in proving his general theorem is to prove it for Jacobians of curves. The Mordell-Weil theorem then follows for all abelian varieties. So let's consider Jacobians, which is, of course, what I want to do because I'm interested in thinking of how abelian varieties are great tools for curves. So, Jacobians. K is now a number field. C, a smooth projective curve of genus G, defined over K, and it better have a K-rational point. Otherwise, the slides will become a little more complicated. And the abelian varieties we'll focus on are, as I say, the Jacobians of curves. And how do you define them? The Jacobian, I'll call them JC, of the curve C is the abelian variety over K given in any of these ways. You can view it in the spirit of Weierstrass, at least when the base field is C. Now, what does Weierstrass do? What would Weierstrass do? He didn't do it, actually. But in the spirit of Weierstrass, you might consider the idea of integrating a regular differential on the curve over a loop, the loop defining an element in H1 of the curve with coefficients in Z. And the regular and the integral of the regular differential maps the element gamma. If I send the element gamma to the integral of omega over gamma, what I've done is I've embedded H1 of CZ into the dual space Hom of H0 of omega, regular differentials of the curve, into C. So I get a complex vector space of dimension G because there are G regular differentials, and I get a lattice of rank 2G because that's the rank of the homology of the curve. So we get a lattice contained in C to the G. We take C to the G over that lattice lambda, and that will be our abelian variety, at least if we're over C, over the complex numbers. We could also view it concretely, as the Jacobian has the property that for any field extension, L over K, its group of L-valued points, which I'll call JC of L as usual, is the quotient group of the group of divisors of degree 0 on C, defined over L, quotiented by principal divisors. And that's one way of viewing it, and it's in fact one of the most standard ways of using the Jacobian as a tool. But it has its virtue that it's defined for over any field K, not only the complex numbers C, as I just did in the Weierstrass spirit. Or it could be viewed more structurally as pic naught of C over K. That is to say, it's the abelian group scheme representing the functor that sends any K scheme S to the group, on the tensor product, of isomorphism classes of line bundles of degree 0 relative to S over C base change to S. one thing to note is that this map from the curve to pick 0 is a contravariant functor, and in fact it's a functor on all varieties, not only curves. And it's sort of, one way of thinking of it, it's sort of the motivic one-dimensional cohomology of the curve. Or it could be viewed just straight functorially as just the smallest group scene containing C. That is, you consider the universal problem of mapping this pointed curve C, base change to any K-scheme, to any abelian scheme over that base that you base change to. And what you get as the solution to that universal problem, as you get it as it's called the Albanese variety of this curve, base pointed at E. As I write here on the slide, C goes to alb of C, which is an abelian variety, represents the universal problem having the property that any morphism from C to any abelian variety A factors uniquely through this one, where the phi there is a homomorphism of abelian varieties. So that's another way of thinking, and it is the Jacobian. You get the same abelian variety. Now, in this case, the Albanese functor is also a functor on all varieties. It's covariant, and it's sort of the motivic H lower one of C. And what's absolutely marvelous, and what's absolutely, I should look at the time, oh yeah, okay. You have a magnificent duality. I won't do it even writing it, but I'll do it by hand gesture. I hope that will work. Here you have, the first thing to say is the two functors, the contravariant functor pic naught and the covariant functor Albanese, have a weird property that if you do them twice, you get the same thing. That is to say, the Albanese of C is just the Albanese of C, because it's just the smallest abelian variety that C contains. For a similar reason, pic naught of C is pic naught of C again. Those line bundles extend. So look at this. This is kind of weird. Here we have, my left hand is going to be pic naught, and my right hand is going to be Albanese. I take the product of pic naught and Albanese. There it is. It is something. It's an abelian variety of, okay, you can do it. It's an abelian variety of dimension 2G, yeah? Okay. Now, there is a fantastic bundle over that product called the Poincaré bundle, the Poincaré bundle. Now, what property does it have? It's kind of weird. Suppose you fix a point in pic naught, on my left hand, and consider consider that point cross all points in the Albanese, and restrict your Poincaré bundle to that, you get a line bundle over Albanese. Now, as you move the point on my left hand, the point in pic naught all around, you get all line bundles of degree 0 on Albanese. That is to say, the left hand is pic naught of the right hand is pic naught of the left hand. They're both the same in some way. And And that maybe reminds one of what you can do in a more elementary way. That is, they just take a vector space of finite dimension over a field. V, that's my left hand. Take its dual, V star. Now, there is a linear functional on that, and everybody knows what it is. So take a point in the left hand and ask what linear functional it is on the right hand, and move that point around, and you get all linear functionals. So you get, that V star star is V, and similarly. Okay? So that's what we have going here for the Jacobian. But there's another way of thinking of the Jacobian. You're done thinking of the Jacobian in 4 ways. There's another way. And it's more relevant to the Diophantine issues that I want to discuss. It's in terms of symmetric powers. So here's a definition. Sn is the symmetric group on n letters acting on the nth power of the curve C. C cross C cross C n times. You let Sn, the symmetric group, permute the factors. Yeah? You consider the quotient. I'll call it sim n of C, the symmetric, I'll just call it sim n of C, which is C to the n, quotiented by the action of this symmetric group on its powers. And it's a pretty nice n-dimensional projective variety. And there's a clear relationship between sim n of C and the Jacobian. There's just a natural map from sim n of C to the Jacobian by sending any unordered n-tuple that will produce an element in sim n to the linear equivalence class of the divisor of degree 0 in C that takes the sum of the elements of that n-tuple and subtracts n times the identity to make it of degree 0. So we get this map from sim n of C, I call it iota here, to JC. And here's a theorem which is going to play an incredible role in the uniformity issues I'll want to be talking about later. The fibers of this map are rational varieties. That's all you have to know. They're rational varieties. If the n is greater than the genus of the curve C, this guy is surjective. If the n is less than, well, I can't say, n is greater than or equal to the genus. That's, the equality is an important moment, by the way, which I will talk about in a second. And if n is less than a certain number, called the gonality of C, it depends upon what field you're working over, and I'm working over the algebraic closure, if you wish, of C, then this map, sim n of C, is injective. Okay? All right. So what is gonality? Gonality, as I say, is going to be the source of an enormous amount of just the focusing on gonality, if you wish, is the source of a great amount of uniformity statements about in Diophantine analysis. Okay, the K-gonality is the curve is the smallest degree of any non-constant function on it. So, so here I have my curve. Here I have P1. Every time I have a function, non-zero function, I have a mapping that looks like that of the curve to P1. And it has a degree. Now, that degree, I'll call it D if you wish, well, the degree can't be 1 if the curve is not of genus 0, right? So it has to be bigger than 1 if the curve is greater than 0. But what does that degree have to be? Suppose, for example, you have a curve which is cut out by an equation of degree 100. That will give you a map of degree 100 to P1. But I don't want just any old map. I want the map of smallest degree. No? And this is also it's an interesting paper to look at. He introduced it. Riemann introduced it pretty nicely in his theory of abelian functions. Now, what's the connection between algebraic points on C and rational points on JC? So if you have an algebraic point on C, and if you consider the set of, now that algebraic point might be over Q or over some small field, but if you consider the set of all of its conjugates over the algebraic closure of the field over which the curve is defined, you can define a map from that point alpha into JC to be just the divisor class of the sum of these conjugates minus whatever you have to subtract from the origin to make it of degree 0. So here we have a way of considering algebraic points on C of degree D, or a degree less than or equal to D. Now, these are not on particular number fields of degree less than D, but I'm taking any number fields of degree less than or equal to D, and if there's a point on C over that number field, it's going to appear in this set S C of KD, and that set maps to the Jacobian over K. Now think of that uniformity. This set is going to involve all algebraic points of degree D of some sort, and it's mapping to the K rational points of the Jacobian by taking that sum. Okay. Now, we could, instead of doing that for the specific degree of an algebraic number, we could just fix the symmetric power of C. And if the degree is less than that fixed symmetric power, like, for example, n, you could also do the same just by taking the first D coordinates to be these algebraic conjugates and put as many identities in as you need to get it in there. And so you get the image of alpha is not in something that depends upon the degree, but it's is in sim n of C of K. A corollary of the theorem is if D is less than this gonality, the natural mapping is injective. Now this is what I wanted to get to. Namely, this is one of the great uses of Mordell-Weil to control algebraic points on curves. And we have the uniformity feature of this SCKD, which doesn't specify a number field. It just specifies some class of number fields, and they're all contained in a single abelian variety whose rational points we can try to understand. For example, if your abelian variety has no rational points, for example, if the identity is the only rational point, you've got no degree D points of this curve. No points of this curve defined over any field of degree D over K. That's phenomenal, right? Anyway, we're going to continue this. I think this is, yeah. We'll continue. This is a good moment to continue. I'll continue at the end of our winter school, maybe with some comments about computation as well. Okay.
Okay, so we have time for maybe a couple quick questions. If you can raise your hand, then I can bring the mic, or Isabel can bring the mic to you.
Oh, hey. I'm over here. Sorry, I'm in the front here. So I had a very quick question. Oh, right over here.
Oh, there you go.
Hi.
How could he have gotten that microphone? Okay.
Indeed, some sort of magic. Oh, yes. So I had a just very quick question. So you talked about this pick not functor, okay? And whenever the word motivic comes up, I automatically think that's...
Whenever the word...
motivic. Like,
yeah.
Or,
woo.
You know,
Okay.
it's kind of it's an interesting word. So.
I wanted the question.
Yeah, so when I think of like motivic H1, I think of like, yeah, Blavatsky had this theory of motivic cohomology, and so I wanted to know, are these things like related in some natural way, or is it just...
Okay, how about this? Suppose you don't know anything about motives, but somebody tells you that he's tired of considering all these different assorted cohomology theories that supposedly give you invariance about your algebraic variety. So he's interested in this algebraic variety, and you tell him, well, if you take the de Rham cohomology, or if you take the crystalline cohomology, or if you take the Étale, or you think of it over C and you take its topological homology, he might ask, as Grothendieck actually asked, and probably almost in this fashion, I mean, is there some single gateway to all of them? Right? In fact, I think I remember the moment when he asked it, but anyway, I probably yeah. I don't. So, well, what would that gateway be? Would it be another vector space? Well, it would have a lot of structure, because you could get de Rham cohomology out of it. And now we have prismatic cohomology. We have more gateways. Yeah? Yeah? And not only gateways, but more and more cohomology theories that need their own particular gateway. Yeah? So you might think of a motive as the supreme gateway that gives real algebraic geometric or sort of pseudo-algebraic geometric structure to all these linear objects that have to pass through it. Is that okay?
Yeah.
Yeah.
How does one prove that every abelian variety is isogynous to, embeds into a Jacobian up to isogeny?
Okay. What you do is you take your abelian variety and you look for curves in it. And you look for a curve that really wiggles in it. I mean, a really horrible curve. Not piano dance, but big thing, yeah? And take its Jacobian. Yeah? Right? Now, its Jacobian is big because the curve has a big genus, and it will, if the curve wiggles in the sense that it generates the abelian variety in which it sits, that Jacobian will map surjectively to that abelian variety. Now, and then you can invert it that way.
Okay, I think we have another announcement before we go on our break.
Go up to the front. Yes, let's thank Barry first. Thank you, Barry.